So thank you very much. And now Anna, if you take the place.
Thank you. So you can thank me later. Today we're going to talk about speeding up your database. I'll give you some general understanding of how to profile queries and make them faster. So we'll look into what is slow, how to create indexes, how to craft better queries, and at the end I will give you a checklist that you can walk away with for your projects. A little about me. My name is Anna Felina. I organize Confu, which is a multi-technology conference. I also run the user group PHP Quebec, which is 10 years old now. And I also rescue projects with my company Fula. Enough about me. What is slow? One of the problems that I encounter is a multitude of queries. And these often occur when you use loops in order to fetch your results. So for example, if you have picture IDs in an array and you iterate over it, and you run a query for every one of these IDs in order to fetch the information, this can create a large amount of queries. For example, if you're displaying results in a table, for each row you're going to have to fetch all this information individually. So you can reduce the number of queries. There are ORMs such as data mapper or mostly active record that use lazy loading. Now we'll also talk about that. So lazy loading is when you load that data on demand. So every time you request a field or a relationship, you fetch another record. And what you can do is use left join in your queries in order to get all related data in one go. Another way of creating multiple queries is when you have deeply nested code. Now, not all people write like this, but I've seen code such as this. For example, you have a function that executes a query and then passes control onto the next function that will then execute another query and so on. So you can end up with a lot of queries. This is an example for if you have album, pictures album, and so you get the user, and then for that user you get the first album. For the first album you get the first photo, and then you get its thumbnail. So instead of that, you could have used one function, which is much more specific, such as get first thumb, and then you query only once. So what you can do is you can count the number of queries that you execute. You can do it manually by adding custom code before your queries. You can also encapsulate it in a function that will count those queries, so that when you execute your code, you can see how many queries you ran. And if you see something like 60, then obviously you have a problem somewhere, and you can investigate. You can also do it automatically with ORMs. They have listeners, and you can tap into those in order to get the number of queries that were executed. So listeners, they're also called observers. The thing you can do, we'll show examples with MySQL, but most of this advice also applies to Postgres and Oracle. In MySQL you have the slow query log, and the way to activate it is to go to my.cnf, and then you just change a few configs. You turn on the slow query log, you set the threshold, which is, for example, this is in seconds, 0.5, which is pretty high. If your queries are 0.5 seconds, it's quite slow still in most cases, but at least if you see that something is above that, then you obviously have a problem and you have to investigate. So it kind of gives you the biggest problems first, and once you eliminate that, you can lower the threshold and continue testing. And then you set the path to where you want to save the file. It's just a little text file, and for every query that is taking above 0.5 seconds, it's going to log it. And then you can take it and run it with a prefix, which is actually, before I go into the prefix, I will show you an example of a schema. This is, as I showed earlier, users with albums with pictures. So I created a test database that I ran on my computer, so I will show you some benchmarks. We have a user table that has an ID and a name. We have 200 users. For every user, we have 100 albums. And for each album, we have 100 pictures. So this is a total of 2 million pictures, which is not extremely large, but but you can see how it can quickly get out of hand. Let's run a simple query. We want to get all pictures from user number 1. So this is a typical SQL query. We select the picture ID and title from picture, we do a left join, and we apply constraint user ID equal 1. And when I run it on my personal computer, which is nearing its retirement, 38 seconds. So that's pretty slow. I mean, it's not supposed to run for 38 seconds. Definitely above the threshold that we set. Now, why is it so slow? I'm not going to tell you exactly, but we will go through a process and incrementally understand how it works under the hood, and you will be able to reproduce those steps with your own queries in order to find the answer. So we prefix the same query that we found in our slow log. We prefix it with explain. And what it does is it runs the queries, it times it, and it also displays this little thing that I will expand in a minute. Displays one entry for every table that was scanned. So because we use a join, only one join, that means we have our main table and the join table, so 2 entries. We're going to look what those entries contain. They contain the table name that was scanned, the key that was used, and how many rows were scanned for that table. Now what's interesting is that because of the join, we actually multiply the 2 numbers. Because for every row scanned in album, we have to scan all the pictures. So we're actually scanning 40 billion rows. And this is why it's taking 38 seconds. And that number will grow exponentially as you add more tables. So if you add another join with another 100 records, or say 1 million records, then you're going to end in trillions. It's going to be awful. You probably will never get to see the result before you die. So we're going to use something called indexes. You'll know how to use them. In case you don't, metaphor is you can flip through all the pages of an address book in order to find the phone number you're looking for. Or you can just pull on the tab for the letter, for the last name of the person, and then you can find it much more quickly. You don't have to flip through all the pages from the beginning. So we're going to add one index. We're going to evaluate the result. We add the table, we add a primary key and album. The same query is going down to 2.38 seconds, which is basically saving us 36 seconds on every single query. So what happens under the hood? We only scan one album because we added an index on the ID. And multiply that by 2 million, only 2 million rows are now scanned. So we found our index right away, our album right away. So instead of 40 billion, we're now down to 2 million rows now. We can add a better index. We can add an index on picture.albumID. The same query is now down to 0.12 seconds. So this is 317 times faster than the original. And so I checked the different speeds of different animals, and this is roughly the difference between a turtle and a gazelle. Just for reference. So what happens with that last index that we added? We have scanned only 200,000 rows because we scanned 20,000 albums and 100 pictures. Now, just because you have an index doesn't mean that it's going to be used. And you can see here that on one side there's no key being used, and on the other side we use one. So you have to think about which index to use. And if you add just indexes on everything that might be useful, then you add an overhead, and you add a latency when you update or create new entries in your database. So we're going to add an even better index on album.userid. Same one down to 0.10 seconds, which is still another 17% increase in speed, which can be considerable multiplied by the number of requests that you have. And there's ways to optimize it even further, but I'm not going to talk about how to configure your database. So the details of that is we scan only 100 albums and only 100 pictures. So it's only 10,000 rows. And here we use 2 indexes. See, we use the user ID and album ID. This is why it's so much faster. What we've learned is that Some of the best indexes that we can use are foreign keys. Now, they're not automatically created. Indexes are not automatically created on foreign keys in Postgres, but you can add them yourself. And also, whatever you use for joins and wheres, if it's also indexed, then you can use that. For example, if you query often on the postal code of your users, then you might want to index that as well. So just try different variations and see what works best for you. So if I have some time at the end, I will talk about how to select index candidates, if I have time. If not, we'll just skip that for now. So should we optimize further? I mean, we're already quite fast, but remember that your database server has a limit. It's the number of queries that you can run per second. And I will give you an example with airport customs. So when you land in a foreign country, you have to go through customs. For example, you have 5 customs officers, and it takes 1 minute to process each traveler. So to look at the passport, ask the general questions: what's the purpose of your trip? Put a stamp, next. So if you have 5 travelers per minute, then your circulation is fluid, right? They just come in, they get processed, and they get out of the way. But if you have 20 travelers per minute, then you create a queue. It slowly builds up, and it just builds up infinitely. So every next person is going to have to wait longer and longer in order to get processed. If you get 1,000 travelers per minute, then if you have the bad luck of arriving on the 2nd minute, you're going to have to wait 3 hours in order to get through customs. So the short answer is microseconds count. You have to speed up your queries as much as possible, because when you have a lot of traffic, that is when you will see a difference. So some more tips. You have to create smaller indexes, which also makes your queries faster. A big int as an index is obviously smaller than a tiny int, but then you want to be able to store a lot of values in it. So if you use unsigned, you can double the maximum value of your numeric keys. Because, for example, if you use a tiny int, if you don't use unsigned, then it's going to go from minus 127 until 128. Or is it the other way around? Anyway, but if you remove that, you go from 1 to 128. What is it? Is it 256? Yeah, because it just doubled. So that's it. And tips for better queries. So you can also change something in the way you structure your queries in order to get faster results. For example, avoid using functions on an index column, because when you use that, when you use a function, the index gets ignored. For example, if you have a create date, so you want to query all your pictures that are from 2011 and higher, then you will use a year function on your column, and if this column has an index, it's going to be ignored, because once it starts manipulating the data that's inside, it can no longer use the index. You can also limit. If you just limit your results to 25, because you're not going to display more than 5 by 5 on your page, then there's no point in querying more than that. So you just limit 25, and now we're down to 0.0009 seconds, which is another 100 times faster than the previous query. So you see, it's really an order of magnitude. I see some people smiling and getting all excited. All right, some other constraints that you can use. Between, so you can select a range between indexes 26 and 50. This is going to take 0.023 seconds, a bit slower, and if you don't use an index, you're not going to have any gain, right? So the columns that you use in the where have to be indexed in order to get the speed gain. More constraints, you can use in, so you have specific IDs that you want to query. Like I showed in the example earlier, picture IDs. So you will extract them first and then fetch information for each one of them. But instead of building a loop, you will just use in and throw these indexes inside, and you will get a proper set, which will take 0.048 seconds. But once again, that's on my slow machine. On the server, it's going to be way faster. You can also split your tables. MySQL can partition your tables transparently. So you can create multiple files on your disk, and it shows data as a single table. So it splits by whatever you specify, by date, and then it's much faster to find your data by your index, and it's still showing as one single table. MySQL archive storage engine, there's various storage engines that people overlook, and this one is not to be underestimated. So the archive doesn't support update or delete, but it's very fast for select. So some of the use cases for that is you can archive old transactions, old news, old blog posts, whatever you use, something that you don't need every day. Just put that in an archive and you query it only when you need it. It's very fast. You can also split databases. It's also called horizontal partitioning. Some people call it sharding. The way it works is basically users, say 1 through 1000, are going to have all of their data in database 1. So they're identical in structure but contain different data. So everything for that user is in database 1, and 1001 through 2000 are in database 2. So when a user logs into the website, you can just point them based on their ID. Once they're authenticated, you point them to the right database and they just deal with that. They don't have to go outside unless they're viewing data for other users. But they can manage their own photos much more quickly. Obviously not going to use just 2 databases, you can use multiple. So, checklist. You're going to count your queries. You have to log the slow ones. You have to use explain and check the number of rows that were scanned. See if there's a problem there. If you get to something like 40 billion when you're supposed to get only 100,000 or less, then you want to try to investigate why it's so slow and how you can help. Try different indexes, remove the ones that are unused so that you don't have index clutter. You don't want to end up with too many indexes and then have the reverse result. Use smaller indexes whenever possible, preferably numeric. Don't use functions on index columns if you want the speed gain. Limit the number of results using either limit or between or other functions for that. And you also want to split tables and databases. You can add to this checklist yourself as you learn new tricks. So just start with that. You have something that's really slow. Yes?
Yeah, I just wanted to stress that first thing in the list, count queries.
Yeah.
It's really frequent with lazy loading.
Okay, so just for the sake of the camera, you wanted to stress that you have to count queries when you have loops with lazy loading. It does create a lot of unnecessary queries. And with my last example using in, you can do one query for the search and then another query to extract the information in one run without having to go back and forth between the server. So that's pretty much it. So I guess I will have time to mention how to properly select indexes. I'll just activate my bonus slide. So this is my bonus slide. Alright, so what's the criteria for selecting a good index? First of all, don't use too many, and test with and without indexes to see if it's actually faster, if you have a gain. Because, I mean, sometimes it looks obvious, you try it with an index and you just slow it down for some reason.
You can retry the explain query with the index.
Yes. So you test, when you test, make sure that you prefix your query with explain to properly time it and also to see whether the index was used and how many rows were scanned, and you compare the results. So always have a before and after and compare, and that's actually the proper scientific method to do anything. change frequency, so you have to know how often your data changes. If your data changes way too often, there's no point in indexing it, because then you will create a lot of overhead, and you don't want that. Selectivity, how many different values you can have for any specific column. And I see people frown, so I will explain that. For example, if you have a column where all the values are different, that's a good thing. If you have a column where there's one or two possible values, like gender, then adding an index on that is pretty much pointless, because you're going to scan half of the database anyway, but the index adds an overhead, so you're not really having any gain. I'll give you an example in real life. You are delivering mail, so you have to deliver mail, so you have to walk on the street with your letters, and you look at the addresses, and you have to deliver a letter for every second house, basically, okay, because 1 out of 2 needs to have a letter delivered. It won't make sense to get into your truck, drive to the 2 houses up, and then get out of the truck and then put the letter, because then you'll destroy your starter for the car. That's a real life scenario. Yeah, so it would be much easier to just take the pile of letters and walk by the street and put one in every second house. So this is the same with database. You have to make sure that there are enough different values so that it will make sense to create an index. And I'll show you a good example on user.id. That makes sense. Picture.date also makes sense, because in the context of this application, you will probably be uploading multiple pictures on the same date, but since you have so many different albums, it's going to eventually split, and you'll have many different dates, which would make the indexes much more efficient in that case. A bad example, as I said, user.gender doesn't make sense, and picture.views also doesn't make sense, because it's something that updates very frequently. So you want something that is a value that is relatively stable, it doesn't change much, and many different values that are possible for that column. And this concludes my presentation. I'll just show you some further reading. You can read up on storage engines in MySQL a little more, and there's a good blog post about sharding. So that's the horizontal partitioning for your databases. If you want to look into that, I will post the slides, and I will tweet about them, so you can just follow me here. You can send some feedback to my email, whatever you like, what you didn't like, what you expected me to cover, and it makes for better presentations for myself as a speaker, but also for the group. And that's about it. If you have any questions.